Hello, I'm Martijn Reicher. I'm a senior software developer at ZettaScale, and today I'm going to be talking about using shared memory in combination with Cyclone DDS and how this will improve the speed of your local data transfer, because you won't be copying any data in your memory anymore. So first, a quick recap. Cyclone DDS, or DDS in itself, is a shared data space, and it's data-centric. It follows a publish and subscribe model, so you only receive data that you're interested in, and it also uses dynamic discovery. So no input from your user is necessary to be able to see other nodes on the network. You don't have to log into servers, any of that business. So with that out of the way, why should we use shared memory in DDS? Well, first, if you look at the schematic on the diagram on the right here, with the normal DDS data flow, or normal Cyclone DDS data flow, data is being copied at each fat arrow, basically, in this diagram. So data is being copied when the user modifies the data, when it's handed over to DDS for writing, then it needs to be serialized to a common data representation format. Then it's written to the network, then it's being read from the network, and that is times the number of instances, so the number of readers on the network that you have. Then it needs to be deserialized again from the exchange format, being read, and then being represented to the user as a sample again. So this is a significant number of copy steps, of course. Now, shared memory at a system level will assign a pool of memory, which is shared by instances of Cyclone DDS. It will have writers take a block of memory from this pool. The user can then modify this block of memory, and then when this is written by Cyclone DDS, the readers on the same system will be notified of this written block. The readers will then present this data to the user, and when the user is done with this block, so when the user says, well, I no longer need it, it signals again to the pool that this block is no longer used, and then it's returned to this pool. Now, if we use this principle of data exchange, so we move to the schematic now on the right again. So you have this memory pool here, the writer requests a block, the user modifies it. Again, copying data is indicated by the fat arrow here. So when the writer requests a block, and it's written, the only time that data might be copied is dependent on the data model, but it might not even be done. Then the writer returns the block to the pool notifies the reader of a new block, and then again, maybe it's deserialized if the data model requires it, and then it's being presented to the user as a sample. So here, only in an optimal scenario, only when you write to it and you read from the sample, copying data is being done. Now, this will give you a number of performance gains, of course, because you can skip the entire network stack. So no copying into or out of buffers from the network. You have a much lower latency. Also, if samples are in the same layout and there are no indirections in your sample, you don't even need to serialize your sample. And of course, you have negligible overhead from multiple readers, because all that's being carried around is the pointer to this block, and it doesn't matter how large this block of data is that you're basically passing around through your shared memory pool, but you can get like orders of magnitude lower overhead. Now, the next question is, of course, so when should we use shared memory? Well, shared memory, so there are a number of indicators for shared memory exchange. And the first one is that where you have large volumes of intranode traffic, so on the same node. This can either be very high frequency, very large size samples, large numbers of readers, or the product of all of these together. Another thing is that it would be best, or the shared memory works best when you have a low history depth, because all the history that you have to keep track of are blocks of memory, basically, that need to be permanently taken from the pool. So the required size of your memory pool scales with the history that you want to keep track of. Then another thing is, another indicator for shared memory exchange is using simple data structures. So no indirections, for instance, like sequences or strings, because these will mean that you don't need to serialize any of your data. And lastly is that you have the same data layout for all your samples, because if you have a sample that is in C, for instance, if you write a sample that is in C and you want to read it as a C++ sample, of course, these two are not the same. They don't have the same memory layout. So this might give rise to that you need to serialize these samples. So now let's go into some typical use cases where shared memory might be useful. Well, firstly, so if you have, for instance, very large LiDAR point clouds or high resolution camera images, these might easily be in excess of like 10 megabytes per sample and 30 samples a second or even more. Well, if you just use naive copy implementation, so if you, for each reader, you have to copy this data, etc., 300 megabytes per sample will easily strain the resource, the capacity of even more extensive systems. Another thing that you can do with shared memory is to create a dynamically scalable pipeline architecture. So if you take your samples and you pass them through different types of analyses, pass them back and forth, you don't need to do any copying. You have no scaling with data throughout the number of steps or the number of data, of the amount of data that you want to put through these analyses. The analysis needs to be done only once and then it's distributed without copying. And because of using DDS, for instance, you can add or remove producers or consumers or different steps in this pipeline structure. And lastly, you can use different security levels for processes, because normally if you want to have this very high level of copying, very high throughput of copying, normally would say you would run everything in the same process. But with this, you can have you can use the shared memory basically as a fire break, as a demilitarized zone between different security levels of processes. You can have producing processes, for instance, of data that have much higher privileges than consuming processes, for instance, on the same physical system. This is also a very nice aspect that you can use shared memory for. So now, how do you use shared memory? Well, firstly, you need to install ISRIX. You need to have several parts of software, and one of those parts of software is ISRIX. You can get ISRIX from GitHub here at this URL. And ISRIX is a sister project of Cyclone DDS, and is the current shared memory service that Cyclone DDS uses. Now you can either download the installer and install it, or you can compile it yourself, because it's an open source project, just like Cyclone DDS. And after you've installed it, you might need to add it to your path if you compile it yourself. Next, you need to, of course, install Cyclone DDS, which is also an open source project, so you can get it from GitHub at this URL. You'll need to compile this, if you compile it yourself, with the shared memory flag set to enabled, and you also need to add it to your path then. And then next you will compile your program that uses Cyclone DDS. And then lastly, before you start your program, you need to start the ISRIX service, which is called Rowdy, so IOX-Rowdy. You need to start this to be able to basically have the memory pool running, because without your memory pool, of course, you won't be able to use the memory pool. Next, you will need to configure Cyclone DDS to use the memory pool, or to use shared memory. And this is by setting the shared memory, so for the shared memory block, for a domain, you set the shared memory enable flag to true, and you can optionally set a log level for the shared memory as well. This is an optional field, by the way. Oh, so let's go back. This is an optional field for the configuration for the shared memory, but you can set a different log level if you want to. And then you set these, so this is an example of this XML file, and you set this through the environment variable Cyclone DDS_URI. This is what Cyclone DDS looks for when it needs to look up needs to look up configuration settings that are different from the defaults. So next, you will also need to configure ISRIX. Now, your ISRIX configuration files, these determine the memory pool layout. And this is very important because this is something that will be this is what really depends very heavily on your use case. So you will need to, your memory pool basically is divided up into a number of segments, which of a certain size and a certain count. So you have in this case, you have slightly over 1 megabyte and 500 of these segments. And the issue is that this is the smallest quantum of memory that ISRIX can give out. And because of this, this segment of memory needs to be 64 bytes larger, 64 bytes because of certain metadata that Cyclone DDS adds on top of the sample that's being exchanged. It needs to be 64 bytes larger than the maximum sample size that's being exchanged. And the number, of course, depends on the use case that you have. So it depends on your history, how many of these samples you're going to need to exchange. Because if you run out of these samples, Cyclone DDS will need to wait for one of them to become available before it can write the next sample to shared memory. So you also always need to have a certain safety margin to make sure that you never run out. And of course, you will, if you start ISRIX Rowdy with -C and then the name of the config file that you're using, you can set this memory pool to a custom configuration. Now, next, also one thing that you can do to get the most out of your shared memory is to use the correct data model. You can optimize your data model basically for shared memory exchange, because shared memory exchange works the best when there are no indirections in your data model. And because indirections cause Cyclone DDS to require to serialize the data. And with indirections, I mean things like container classes or strings. So strings and sequences, optionals and externals, these kind of classes are indirections. So a string, for instance, you can replace a string with a fixed size array of chars, or a sequence you can replace with a fixed size array of objects. This might not be as efficient in certain regards, but this will allow Cyclone DDS to basically know the size of this struct or the size of the objects that's being exchanged at compile time, basically, and therefore it can get the memory layout, etc., complete, basically, and it can exchange them without needing to serialize the data. Another thing is that this is mainly an X-type thing, but you only can use final types, because if you start changing the ordering of your fields, for instance, in your data model, then also you require serialization. And lastly, you can use the loan mechanism. Now, the loan mechanism is something that's a DDS thing, and it allows you to use pre-assigned samples, so samples that are pre-assigned and whose lifetime is managed by the reader or writer that's handling these samples. And this removes the copy step when you hand over the data from basically your program to Cyclone DDS, when you transfer the data from the user space basically to the DDS space. Now, for writers, you can request a loan by using DDS loan sample, and then you can say, well, I want an X amount of samples. And this sample, the ownership of the sample, is then returned to the writer with a call to DDS write. And when you use the shared memory pool, this writer then takes the sample from the memory pool before it starts even writing, and the thing that you're modifying is this sample from this memory pool, basically. At the moment for C, this implementation is still in progress for the reader side, so I won't go into that any further, but it's also a mechanism for the readers according to DDS spec. There are also a number of limitations for using shared memory in Cyclone DDS. For instance, as soon as you add internode communication, so as soon as you start communicating with other readers that are not on the same system or that are not using shared memory, then of course you will add network communication to the network communication steps, and therefore you add or you remove many of the performance gains that shared memory will give you, because all of the overhead of network communication going through the network stack, serialization, deserialization, all this kind of stuff, all of a sudden gets introduced again. Another thing is that you might find that using simple data structures might be a limitation. The fact that you cannot use indirections, for instance, if you want to get the best performance out of your shared memory use or out of your DDS usage. Next is, of course, you also have a memory pool, so you have a limited number of resources, and you need to set this resource limit at the start of running your shared memory pool. So you also need to know this in advance. And lastly, you have the reliance on ISRX as the shared memory medium, because ISRX is not available for certain OSs or certain hardware combinations, or might be that it might not be to the security levels or certification levels that some users might want. Now here in this diagram, I have some typical performance gains with one writer and one reader, comparing what you see with shared memory and what you see with a loopback. So the shared memory is the purple and the green one, and the loopback, so the network exchange, is the yellow one. And this is just on a virtual machine, so this is just an indication of what you can get as performance gains, but this is for like real life systems where it's running on directly on hardware, etc. We're not limited by a virtual computer or virtual system. You might get much better results. So for instance, firstly, what you can see is so this is basically, this is created using the throughput and the SHM throughput or shared memory throughput examples that are part of the Cyclone DDS code base. And what you can see here, so the blue and the purple lines are is the throughput in messages per second. So on the left side, you have the throughput in megabytes per second, and on the left side, you have the number of messages per second. Please note, by the way, that these are logarithmic scales. And at the bottom, you have the message size in bytes. So if you look here, you can see that even with very small messages, the amount of the throughput that you can get, both in bandwidth and in messages per second, is significantly larger for using just shared memory exchange than using the network exchange. And you can see here also, so the green part is the throughput in bytes per second, or no, megabytes per second, correction. And the yellow one is for loopback, and the green one is for shared memory exchange. And you can see that for small messages, there is some difference, but it's not huge. But the larger the messages get, the larger the difference gets. And you see that for around 32 to 64 kilobyte message sizes, the loopback interface starts to saturate at about, 1 gigabyte per second approximately, while the shared memory exchange keeps chugging along at up until like 50 gigabytes per second. So there's a huge difference that you can in performance that you can see between shared memory and normal exchange. So next, I would like to show you some real-life demonstration. Now, this is just a comparison of the throughput and the shared memory throughput examples that come with Cyclone DDS. And this is with 1 megabyte samples, and we will see what the performance is on this. Well, this is on a virtual machine. This is the same virtual machine that I did the plots that you saw previously on. And at the same time, we'll also be looking at the ISRX introspection client, which is a utility program that comes with Cyclone with ISRX. And we can also explore what's happening inside ISRX while the shared memory exchange is running. So going to this demonstration. So we have here. So let's So this is IcerX. So you can see here, we're starting up. Let me make this a little bit larger. So we're starting up Rowdy, and we're giving it a configuration file, IOX CFG, which is this guy. And you see here that you have a whole memory pool of all different kinds of segments. We have here 320 bytes and 400,000 or so segments of that size. So this is 1 kilobyte plus 64 bytes and about 100,000 samples of those, etc., 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 etc. So this is the configuration of the memory pool that we're going to be using. So going to here, go to here. So we start IcerX. Needs to think a little bit, and now it's ready for clients. Now the thing that we're using here is the introspection client. So here you can see which processes are subscribed to, or communicating with IcerX. And at the moment, this is mainly just IcerX itself and the introspection client. So now we will be looking at what happens when we go use shared memory exchange. And this is for 1 megabyte sample. So here we have the publisher, 1 megabyte samples. Okay, waiting for a reader. And now we have the subscriber. So it's waiting for samples. And now you see here. So this is basically, you can see here that we get about 3,000 samples a second and about 20 to 25 megabytes per second. This is wrong. Okay, this is something that's wrong in the example. Okay, but you can see here that we get about much larger throughput than you would expect from just the normal network interface. And as you look here now, if you look here now, you can see that this is, so we have here, as a publisher, we have Cyclone DDS that's signed into IcerX, and you have here a subscriber as well. So these are the two different throughput examples that are running. Now, if we also look at the memory pool usage of IcerX, then you can see here. You see here that the number of chunks in use, it's going up and down, but there's approximately like 20 chunks or so in use of the 1 megabyte samples. And this is basically the memory pool usage that we have at the moment. And that is being used by these two programs to exchange the data. Now, if you compare this, so let's exit this. Now, if you compare this with the normal throughput, so we have here the normal throughput, so without shared memory. And here we have the normal throughput. So what you see here now is that you get, well, 80 or so samples a second, 60, 70, 80. Of course, yeah, this is a virtual machine, so it's not as nice as I would like, but you can see here that we start to plateau out at about, well, something going on in the background. Okay. Just let me restart this. But yeah, you can see here that you have approximately like 60, 70, 80 samples a second, 700 megabytes a second or so of data being exchanged with just the ordinary network throughput. Now, this is, so here we have the configuration file. So this is like a typical configuration. This is the typical configuration file that we're passing through to Cyclone DDS. So this shows you that, oh yeah, we need to enable shared memory and the log level is set to info. So yeah. There you go. Yeah. So, are there any questions with this?
Thank you, Martijn. I don't see any questions in the chat yet. If anybody has some questions, please write them in the chat now. Martijn, would you want to go over a few of your slides again? I think you, just in case you want to add a few more things, we still have quite a bit of time.
Well, I would say the thing that you can see from just this simple plot, you can already see that even for like only 16 byte samples that you're exchanging, you can already see that shared memory exchange is way quicker than going through the entire network stack. You can already see that you get maybe 50,000 or so messages per second at the most, while the shared memory exchange tops out at about 100,000. So even if maximum throughput but if you're talking about megabytes per samples is not necessarily your goal, even the lower latency and the higher responsiveness basically of this process, of this exchange medium, it make it worthwhile to use shared memory exchange at this level. And another thing is, of course, that simple data structures are a suggestion; they're not a hard requirement. You can also use indirections in your samples that you want to exchange, but again, then it needs to be deserialized at the writing and the writing and the reading end. Then you won't get your best performance. But if you really require these kinds of structures in your exchange samples, then it is possible. You will give away some of your performance gains that the shared memory might give you. So that's several points that I would go into. I don't really have that many other questions to go. That many other things that I would really put any emphasis on. I would say if you have any real big questions, or if you want if you don't get it working, or if you have some real bugs or something, please contact us, or please join us on GitHub and start contributing or giving us your issues, because together we can make the product better. Please help us make it better for you as well.
Yeah, and after we end this webinar, you will receive the recording of this session by email, and you'll also receive a link to join us on Discord, where you can talk with us directly, obviously. And if you have any questions, feel free to get in contact, like Martijn said. With that, I think we can end this webinar and see you next time.
Mm-hmm.